Okay, well, welcome back and happy Monday to all of you. We are moving on from chapter 14. If you have questions or concerns about the computational assignment, I've been trying to do it myself and I kind of got stuck on problem number 10. So if you get there and you're having trouble, stay tuned. I'll provide more details in a little bit. All right, so moving on to chapter 1. Chapter 1 contains a lot of stuff that's review of sort of introductory organic chemistry. So we're not going to discuss a lot of these things in class in a lot of detail. Be familiar with hybridization, sigma and pi bonds, resonance, electronegativity, and so on. But we won't talk about that in a lot of detail. What I did want to do is just briefly contrast valence bond theory with what we're going to be doing with molecular orbital theory. And we've talked about molecular orbital theory a lot in terms of the math behind it. Valence bond theory is a little bit simpler on the surface. The folks responsible for it are listed here, and Pauling is probably the most famous. The idea is that you assign electrons to individual orbitals on atoms, and then binding energy comes from exchange of electrons between the two atoms of a bond. So two electrons in a bond, and the stabilization comes because they're being shared by two nuclei. And we have this idea that bonds are localized, electrons are localized in the region between two nuclei, which, if you remember from chapter 14, we totally gave up on that idea because we said we were going to allow an individual electron to contribute to all of the orbitals in a molecule. But if you're going to do this, if you're going to make bonds between two atoms, and you're going to make the electrons occupy the space between those two atoms, then suddenly geometry matters a lot. You need atomic orbitals that point in the right direction to be consistent with the observed geometry. And Pauling's solution to that was hybridization, the idea that you're going to mix the available s and p orbitals in various combinations to get sp type hybrid orbitals. And the I here on that SPI is called the hybridization index. Now, one thing I learned when I first read this chapter, I didn't really know, and that is that the familiar hybridization indices, SP, SP2, and SP3, is not all there is. So, for example, tetrahedral geometry, each of those comes from a hybrid orbital on carbon that we say is 75% P and 25% S. We call that sp3. sp2 is consistent with 120 degree bond angle and 66% P, 33% S, and then sp hybridization 50% P. Oh, we got to move the little box. I'm sorry about that. Thank you. SP hybridization 50% P and 50% S. And that works, but it turns out these numbers don't have to be integers. There's no requirement for that. All those numbers mean is these numbers give you a sense for what percentage S versus P each orbital is. So, in a broader sense, hybridization index, no, we don't want a crash report for Adobe desktop services. The hybridization index can be something else depending on what this bond angle is. And more broadly, it's defined as -1 over the cosine of the bond angle. The minus is because all of these bond angles presumably are greater than 90 degrees. So if you don't want a negative number. Anyway, let's look at some molecules that have non-integral hybridization indices. So in ammonia, you can measure the bond angle. It's 107. And so you can't account for that technically with just sp3 hybridization. So if you put that bond angle into this equation, you end up with hybridization index of 3.4. That is, each of these bonds comes from 77% P and 23% S. And you can do the math based on the understanding that you had one 3p orbitals to start with and one s orbital to start with, you can do the math and conclude that the lone pair is in an sp2.1 orbital. That's 32% s and 68% p. Contrast that with just methane, where if you considered ammonia to be sp3 hybridized, that lone pair would be in a 25% s orbital. In ammonia, it's in 32% s. And that makes sense when you think about the fact that s orbitals penetrate to the nucleus. So unlike a p orbital that has a node at the nucleus, right? The s orbital, if the nucleus is here, actually has a non-zero wave function value at the nucleus, which means that electrons in s orbitals experience the nucleus more. They have a bigger attraction to the nucleus than do electrons in p-type orbitals. So it makes sense that this lone pair would have a higher percent s because it's not being shared between two nuclei. So in order to stabilize it more, we're going to increase the s hybridization. Similarly, with water, the bond angle here is even tighter than 109.5. So though you've often thought in the past, perhaps, of water being roughly sp3 hybridized, actually, if you do the bond angle, it's sp4 hybridized. Now, if you think of hybridization as just describing how many p orbitals you mix with the s orbital to get the new orbitals out, that's not going to make any sense because you don't have 4 p orbitals to mix in. But remember, that index just comes from the bond angle, and it tells you it's the orbitals that we use to make the hybrid orbitals we have in this bond between oxygen or hydrogen are 4 parts p to 1 part s. That's just percentages. So these orbitals are 80% p, 20% s, and then the remaining 2 lone pairs are in a 30% s, 70% p orbital. Again, it makes sense for the lone pairs to be in orbitals with higher s character because they will penetrate to the nucleus more. It is fine for you to think of orbitals with higher s character as being more electronegative. That works fine. And in fact, we'll use that argument later. You'll recall, some of you who are TAing in organic chemistry, you're going to have to explain to your students why the pKa of like a hydrocarbon like methane is like 50, whereas the pKa of an acetylene is 25. And that has to do with the fact that the carbon of acetylene is sp hybridized, has more s character, so the electrons that are left behind when this proton is removed are held lower in energy than would be these electrons. Okay. Yeah.
So we've talked about this recently in OChem, and then we're talking about like drawing orbitals and stuff.
Yeah.
Why is this like not important enough to clarify this distinction in previous chemistry classes?
Why is it not important enough to clarify the distinction in previous chemistry classes? I would say because the difference between 109.5 and 107 and even 104 is small enough that it probably doesn't matter at that level. And honestly, I almost feel like this is sort of gee whiz because we're not going to come back to this hybridization index that much, if at all. So it's sort of I would say it's maybe a nerd credential. There are some things in science that if you know about, you feel like a little bit more nerdy or more important than other people. So we're initiating you into the nerd credentials of organic chemistry. Yeah. Later on, we're going to see an MO theory explanation for why geometry of molecules changes, and it's always about getting high energy electrons into a little bit lower energy orbitals. So that principle is useful. Yeah, what else? So valence bond theory is great because it focuses on things that change in reactions. It's the bonds that are changing in reactions, and so that's useful. But it's incomplete without the concept of resonance. So resonance is really a valence bond theory concept. The idea is that, say, in this anion, the negative charge is shared equally between oxygen 1 and oxygen 2, and that the real structure is some hybrid between the two. Some of you in teaching the sophomore organic class are going to try to tell people to draw hybrid structures, and depending on your instructor, that's fine. Some people will do something like this, and then a partial negative here and a partial negative there. I hate that because we lose track of the electrons. And in a lot of cases, OChem is about counting electrons and following them. So I honestly prefer just drawing both resonance structures. As long as you have in mind that the charge isn't hopping back and forth, it's actually in both places at the same time. In valence bond theory, each resonance structure is an incomplete description of the actual structure of the molecule, and you get stabilization from resonance. So another classic example is, of course, benzene, which we draw like this to communicate. Oh, no, just the same thing. We draw like this to communicate that benzene doesn't have 3 double bonds and 3 single bonds, but rather 6 equivalent bonds. And that the electrons are delocalized over more than just 2 atoms. So that's the important concept of resonance, and without it, valence bond theory doesn't explain a lot. Let's see, there was a thought that I thought was important, but now is gone, so it must not have been. All right, so MO theory, in contrast, doesn't actually need the concept of resonance because delocalization is baked into MO theory. As an example, if you do molecular orbital theory for the pi electrons of benzene, and we're going to sort of look down on benzene from the top, you would see that the lowest energy orbital looks like this and has, oh man, gotta choose my colors carefully. Let's go here. You've got a lobe above the ring, a node within the plane of the ring, and then below the ring you've got another lobe with this. And so those are pi electrons. This is the lowest energy orbital in benzene. If you do molecular orbital theory, the lowest energy pi type orbital. And those are delocalized across all the atoms, right? And then there are some others that we could draw, and maybe we won't do them all. I'll draw just a couple of them to give you a sense for what they look like. But there's one that looks like this that envelops sort of half of the molecule above and below the plane of the ring. There's a phase switch in the middle. You've got, and here color represents sign of the wave function. Anytime color changes, you're going through a node. So we're looking down on the ring from the top. Wave function has one sign, is maybe positive here and negative down here. There's also a switch in wave function sign here. So that's what another one of the pi type orbitals looks like. There are 2 of them that are equal in energy, and we'll talk about this actually later in chapter 1, so I won't draw them any further. But MO theory doesn't need resonance because in MO theory we give up the idea of a bond being 2 electrons shared between 2 atoms. In fact, if you ask people that are really heavy into molecular orbital theory about bonds, they'll look at you and say, bond? What is this bond you speak of, right? So MO theory does a great job of handling electron delocalization, but as the molecule gets bigger, it gets more and more complicated, more and more difficult to keep track of what's changing. And so we're going to use a hybrid of valence bond theory and molecular orbital theory that will allow us to focus on bonds, but will allow us to also account for electron delocalization. I will say that Valence bond theory and molecular orbital theory can get us to exactly the same place, and they can be interchanged easily with maths. So in your Gaussian assignment, there's going to be a place where you click a box or select something from a drop-down menu that's going to change the calculations and do it in terms that give you localized orbitals between individual atoms. So you can get interchange between valence bond theory and molecular orbital theory and get the exact same answer. So since we can do that, we're going to pick and choose how we see molecules in ways that will make sense to us. Yeah?
So in reality, is it somewhere in between the two?
In reality, so what is reality? Question is, in reality, is it somewhere between the two? I guess I would say that I think Dr. Asplin says this maybe. Theories are just models, and all models are incorrect, just perhaps in different ways. And of course, we haven't yet been able to ask a molecule about itself, so we don't really know what reality is. What we know is whether or not the data are consistent with our model. And for right now, I guess in the past I've been tempted to say, oh, well, valence bond theory is incomplete without molecular orbital theory, but actually they're just two different theories that describe the same thing in different ways, and we will pick from both concepts to explain what's going on with molecules. And our goal here is going to be to develop enough chemical intuition that we can make sensible predictions about organic molecules when we don't have a computer available. When you're just drawing things, can you make some sensible predictions? Yeah, what else? Sorry, Samantha, I think that was a totally unsatisfying answer to a good question.
That makes sense.
All right. What else? Okay, so your text takes you through something it calls QMOT. Since we like acronyms, we don't like acronyms in OChem as much as the biochemists do, but we'll use a few of them. QMOT is qualitative molecular orbital theory. Qualitative because we can do this with a pen and paper. You don't need really any math at all. There's going to be some principles that we talk about, that we outline, and then I'm going to show you through the rest of this chapter how you can use them to get some very accurate pictures of bonding in some simple organic molecules. So principle number one is focus on valence electrons. Duh. For most cases, when we're dealing with carbon, nitrogen, and oxygen, we're going to forget that there's two 1s orbitals down there. Only worry about the valence electrons. Principle number two, we're going to make completely delocalized orbitals, molecular orbitals, as linear combinations. That means some combination of adding and subtracting with weighted coefficients of the available atomic orbitals, which are going to be, depending on whether you're dealing with hydrogen or carbon, the 2s, the 2px, the 2py, the 2pz, and then maybe the 1s orbital if you're dealing with hydrogen. Sorry. Okay, fine. I need to remember not to write off the page because it doesn't like it when I do that. 2py, 2pz. Okay, so you've got a starting alphabet of orbitals. We're going to combine those together to get molecular orbitals. Remember that 2p, y, and z are 90 degrees apart with respect to each other. That'll be important later. All right, so what do these MOs have to look like? Well, there's a symmetry requirement. They have to be either symmetric or anti-symmetric with respect to the symmetry of the molecule. All right, symmetric versus anti-symmetric. I'll try to show you what that means. in just a second. But what do we mean with respect to the molecule symmetry? And actually your text says symmetry operators. I wasn't going to say that because when I hear symmetry operators, I get scared and my mind goes blank. But it's not as bad as you think, and we're not going to go as deep into it perhaps as you did in PChem or inorganic chemistry, because I don't really understand point groups or symmetry groups or anything, so whatever. What are some symmetry operators? Well, one might be a rotational axis, right? So if we have this trigonal planar molecule with 120 degree bond angles, and now I need to draw it on the side because it's hard to draw 3D in a 2D plane, but here you go. Imagine 120 degree bond angles. We have an axis of symmetry where if we rotate around this axis by 120 degrees, we get the same thing. So this is actually called a C3 axis, right? All of these molecules also have this molecule also has a C2 axis. If you imagine rotating this molecule by 180 degrees, you exchange the positions of these two hydrogens and you get the same thing. So those are two different symmetry operators. Another symmetry operator is a mirror plane. So this molecule also has a lot of these. I'll just draw one of them, but you can find a lot more. If we draw a mirror plane in the plane of the page, and this mirror plane would bisect, would be aligned with that particular bond. What color am I going to choose? Doesn't matter. So here is your mirror plane, and it lies in the plane of the page, so the hydrogen here would be in front, this would be in back. They are reflections of each other. Mirror symmetry is sometimes called sigma. And there are a bunch more mirror planes, and you can find them. For those of you playing along at home and geeking out about point groups, this molecule would be in the D3H point group. Do I know what that means? Nope. But what this means is when we generate orbitals for this molecule, they have to obey these symmetry operations. In other words, we might imagine that an orbital from this molecule will, if we do a C3 rotation, the wave function sign won't change as we go from here to here, right? Alternatively, we might imagine a situation where the wave function sign does change as we reflect from here to here. So you got two choices, and you can either have the same wave function sign across an element of symmetry or opposite wave function sign, but you can't have you can't have MOs that disagree with the symmetry of the molecule. Now that's a funny requirement. Let me give you just one example in this same system that demonstrates that it obeys this symmetry principle. So methyl carbocation, one of the MOs of methyl carbocation is this. It's a p orbital, and it's above and below the plane that contains the molecules. Let's look at what happens when we do the C3 symmetry rotation. If we spin this molecule by 120 degrees, what happens to the wave function sign? Nothing, right? Stays the same. So this MO works because it is symmetric with respect to the C3. There is a mirror plane, we didn't mention it above, but a mirror plane that coincides with the plane of those CH bonds. So I'll highlight those in purple just to indicate they're in the plane of this mirror that we've made. If you reflect across the mirror, we now have opposite wave function signs. So this p orbital is anti-symmetric with respect to this particular mirror plane. All right, and we'll see that the orbitals we generate are going to obey this principle, and sometimes that will affect our choices. Okay, so principle number 4 is that in generating orbitals for complicated molecules, we're going to make the MOs for simpler high symmetry structures. Then we're going to adjust for geometric distortions or changes. That doesn't make sense right now, but you'll see it as we make these orbitals. Another interesting principle is that molecules with similar structures will have similar MOs. So, for example, if you compare CH3 and NH3, they're going to have similar MOs. The chief difference is going to be the number of valence electrons. There are some other principles that I don't know that we need to write down. Let's see. Total energy of a molecule is the sum of the MO energies of the individual valence electrons. I think that's self-explanatory. There's a principle 7 that I'm going to hold off on because it doesn't make sense to talk about it until you actually have an example. The remaining principles are about combining orbitals together. And these, if we were just starting with chapter 1, these would be somewhat unfamiliar. So I'm just going to make a note that I've skipped talking about 6 and 7, though you can find them in your text. These are going to be familiar based on what we did in chapter 14. So when you combine two orbitals together, you get two new orbitals out. You get a bonding or stabilized orbital plus an antibonding or destabilized orbital. And the destabilization you get, the antibonding orbital is more destabilized than the bonding orbital is stabilized. So we demonstrated that that was the case back in chapter 14. And remember, the idea was you bring two orbitals together, you get the bonding orbital out, you get the antibonding orbital out, and this energy difference of destabilization is bigger than this energy difference of stabilization. So I need a less than sign there. And remember, that was because of the overlap integral, that S term that we talked about. That sounding familiar?
Yeah.
Sort of? Okay. Second, that when you mix two orbitals together and they're not in the same energy, so if we have two orbitals like this and we mix them together, the bonding orbital resembles the lower energy starting orbital, and the antibonding orbital resembles the higher energy orbital. Your text says it this way: the lower energy orbital mixes the higher energy orbital into itself in a bonding way, whereas the higher energy orbital mixes the lower energy one onto itself in an antibonding way. Our classic example of this was, say, an oxygen p orbital and a carbon p orbital. And remember we said that, oh, it's actually exactly the opposite, right? A carbon p orbital and an oxygen p orbital. We said that the pi bond is going to be mostly, the pi orbital is going to be mostly on the oxygen, whereas the pi star is going to be mostly on the carbon. Okay? So that principle we already know. Principle 10 is related to the energy gap between the two orbitals. The smaller that we're mixing together, the smaller the energy gap between the two orbitals, the greater the stabilization between the two orbitals. And 11 is related if there is better overlap between two orbitals, we also get greater stabilization. We interrupt this program with a brief correction. During the lecture, I inadvertently made a mistake in describing the impact of the overlap integral on the amount of stabilization an orbital experiences when you mix two orbitals together. I will now explain to you the correct way to think about this, and I apologize sincerely for misleading you during lecture. I'm very, very sorry. During lecture, we were talking about Principle 11 of Qualitative Molecular Orbital Theory, or QMOT, which is that the better the overlap between two orbitals in space, the greater the stabilization they will experience. A classic example of this is that two orbitals that overlap in end-to-end overlap as in the formation of a sigma bond is more stabilizing than side-to-side overlap. And we'll have occasion to revisit this principle a little bit later when we actually do an example. But the way I attempted to explain this during lecture was actually incorrect. I drew your attention to the experiment, or the thought experiment we did early on in chapter 14, in which we mixed together orbital phi A and orbital phi B into two different molecular orbitals. And as you recall, the antibonding orbital, and I'm not writing the orbital coefficients here, is higher in energy above the position of the original orbitals than the bonding orbital is below that original position. We said that the magnitude of that destabilization is greater than the magnitude of the stabilization that you get from bonding. And in our discussion of that in chapter 14, we said, and this is what I got wrong in lecture, that the energy of the bonding orbital is HAA plus HAB. HAA is the energy of one electron near one nucleus, and HAB is the energy of an electron shared between two nuclei, and then that's divided by 1 plus S for the bonding orbital, and then for the anti-bonding orbital it's HAA minus HAB over 1 minus S. This is written correctly. Unfortunately, I wrote it incorrectly in class. Just to clarify, remember that HAA and HAB are both negative, because having an electron shared between two nuclei and having an electron near one nuclei are both more favorable than having an electron an infinite distance from the nuclei. Okay? And then S in the denominator is the overlap integral, which does talk about how much two orbitals actually overlap in space. And to the extent this number is different from 0, the bonding orbital will be not quite as low in energy as the anti-bonding orbital is above the line where you started. During lecture, I inadvertently said this was a negative sign. And the reason I thought that is because if this number were negative and you increase the overlap integral, then the stabilization would get even better. In truth, what this principle means, better overlap, greater stabilization, is that this HAB integral, the integral that involves sharing an electron between two nuclei, that integral depends on the extent of overlap, such that if we increase this overlap integral, the extent of favorability in HAB is going to increase as well. I apologize for the confusion. I hope what I've said here clarifies that. Don't worry if you're struggling with understanding this math and what we've talked about. My attempt here is to correct the wrong thing I said in lecture today. The principle that two orbitals that overlap more effectively will experience greater stabilization as they mix to make a more favorable bonding orbital. That is a true principle that you can take to the bank. For your attention during this special announcement, we now return you to your regularly scheduled program. Okay, principle 12 is that, I'm sorry, Jasper, before we move on, do you have, does that sort of make sense, or?
Yeah, I'll probably check back from child 14.
Okay, yeah, and if you have questions, come ask me.
Yeah, because I think I'm confused sometimes.
Okay. Principle 12 is that more electronegative elements, I struggle to write electronegative every single time, more electronegative elements have lower energy atomic orbitals, and that's why they're more electronegative, because the electrons in them are held lower in energy. And then that's going to combine with what we talked about up here to generate this picture of bonding between elements that have different electronegativities. That, because oxygen's more electronegative, its p orbitals are lower in energy than those of carbon. So when we mix them together, the lower energy orbital is going to be more on oxygen and the higher energy orbital is going to be more on carbon. So electronegativity is a really useful principle. And then I think I'm going to skip 13 and 14. 13 is that geometry changes that result in large changes in overlap will also result in large energy changes. We'll apply that later. And then 14 I don't think is that particularly useful to us. So years ago, President Ezra Taft Benson gave a talk at BYU called 14 Fundamentals for Following the Prophet. These are your 14 fundamentals for generating molecular orbitals, okay? So follow these principles and don't go astray. Now, can I tell you, I got in trouble once at church. So this was the last time I was ever asked to lead the music in primary. We were learning the song Follow the Prophet, and of course there's a verse about Jonah who gets swallowed by a whale, and so I couldn't resist telling the kids that maybe for that verse we should sing Swallow the Prophet, because that's what the whale did. They thought it was funny, and they started singing that all the time, and the primary chorister was not amused. and her husband's the bishop. So I've never had the opportunity to lead the music in primary since then. So that has nothing to do with what we're talking about, but just be careful. Be careful what you do and say in front of children. All right, so let's start with a simple system. We're going to do this QMOT approach for CH3. And we're not even going to say whether this is CH3 cation, CH3 anion, or CH3 radical. But let's start with the assumption. We're going to assume a trigonal planar CH3. And this is because of one of the principles of QMOT where we're going to start with high symmetry structures and then make adjustments if we need to. So the simplest and highest symmetry structure for CH3 is going to be planar. Now, it might help us in this discussion to establish a coordinate system. So I'm going to say that the up direction is x, that the y direction is out here, and that this direction is z. In doing so, I recognize that I may have run afoul of somebody's favorite coordinate system handedness conventions. I don't know whether this is right or left-handed. I also don't care. That's just what we're going to do, okay? So we're going to imagine a trigonal planar CH3. We're going to have it lying in the xy plane. We're going to have as our alphabet of atomic orbitals 3 1s orbitals from our hydrogens, each of our hydrogens. We're going to have 1 2s orbital from carbon, and then we're going to have 3 2p orbitals. They're each aligned along one of these axes, 2px, 2py, 2pz. That's why we've chosen this coordinate system, so that you can see where each of the p orbitals will be. So now we get to make up combinations of these things, and our rules are only that they have to obey the symmetry properties. So let's think of some.
Sorry, sir. I thought
Yeah.
we were only considering valence electrons.
That's right. But so we're not considering 1s orbitals from carbon. But for hydrogen, the valence electrons would be in the 1s orbital. All right, so here is our carbon, and here is our hydrogen. As I said, it's in the xy plane. So the first thing we might consider doing would be to combine the 2s orbital on carbon with each of the 1s orbitals on hydrogen. And we might consider doing that all with the same phase. So same wave function sign. I'm getting disoriented. Oops, same wave function sign, Joshua. I'm getting disoriented because last year I used pink and yellow, and this year I'm attempting to use blue and yellow for wave function signs. So, ooh. This one is symmetric with respect to the C3 symmetry operator. You rotate 120 degrees and you got the same thing. Does that make sense? When I draw it this way, I guess I should point out that this is more of a schematic that helps us keep track of what everything of the atomic orbitals that we are combining to make this new molecular orbital. In reality, this would look like a delocalized cloud of electron density in the plane of those bonds all over the place. Okay. All right, and if you look at where the electron density is, it would be between carbon and hydrogen, but not between any particular carbon and hydrogen, but rather between carbon and all of the hydrogens. So this would be a CH bonding type orbital, and it involves side-to-side overlap of, it involves sort of end-on-end overlap along axes between atoms. So this is a sigma type bonding orbital. And yeah, and we'd say it's mostly carbon-hydrogen bonding. Now, if we use the same set of components but combine them with a change in wave function sign, we would also obey the symmetry principle, right? If you put the axis through along the z-axis, you still have a C3 axis of symmetry there. So we've got two different combinations that we can make from the alphabet of orbitals that's available to us. Okay, so, and we get both of these ideas from mixing the 2s on carbon with the 3 1s orbitals on hydrogen. And you've got this sort of in-phase combination where the wave function signs match up, and you have this sort of out-of-phase combination where the wave function signs switch as you go from carbon to hydrogen. Okay. What else? So we still have some p orbitals that we have not involved in this process. So let's go ahead and mix the 2px with the 1s orbitals from hydrogen. Let's see what that would look like. And maybe we'll keep our coordinate. I'll copy this down and move it down a little bit lower so that we can remember our coordinate system. So here's one of the CH bonds, here's another coming out of this, here's another going back into the page. The 2px orbital would be aligned along the x-axis, so that would be here. It's sort of hard to draw. I guess what we mean is that this lobe on the bottom bisects the space between the two hydrogens, the one in the front and the one in the back. And of course there's a phase switch as we go from the lobe on the top to the lobe on the bottom. There's a change in, oops, it doesn't work, change in wave function sign. And we can actually overlap those with each with the 1s orbitals on hydrogen in a bonding kind of way. In reality, if we were to draw what this orbital looked like without trying to draw the individual atomic orbitals that they come from, what we would see would be a lobe up here, a node at the nucleus, and then a lobe down here that encompassed both of those hydrogens. So interestingly, if you look at that, it kind of looks like just a regular p orbital with just an inflated lobe on one side that's encompassed those hydrogens. All right. What else? We could come up with the anti-bonding combination here. This is the in-phase combination. I'm not gonna, well, suppose for completeness we could draw the anti-bonding combination. That would just be having everything in the same place, but now the lobes on the p orbital don't match with the sign of the wave function on the hydrogen. So it would be yellow here, then blue, oops, then yellow, and blue. So that would be the out of phase combination. Let's now see about mixing the 2py orbital. Remember, the 2py orbital is going to extend out toward us. So we would draw that. It's kind of tough. You'd have to sort of imagine it coming out toward us this way and then back away from us like that. We'll go blue in the front and yellow in the, oops, that happened last time too, yellow in the back. We can overlap that with a blue 1s on hydrogen in the front and a yellow 1s on hydrogen in the back. Interestingly, the 2py orbital has a node, mix 2py with the 1s's on hydrogen. The 2py orbital has a node in the xz plane. And this carbon-hydrogen bond coincides with that xz plane. So there is no orbital on that hydrogen because it's in the xz plane. Now, if you pause to look at what we've generated so far, go back and check, do they obey our symmetry principles? This one, if you go through and do a C2 axis here corresponding to the x axis, that's symmetric. So is this one. If you use that same C2 axis here, it would be anti-symmetric. So we've obeyed both of those principles. Okay, there's more to say on that, but we have run out of time, so we'll have to pick that up next time. And I do believe I recorded sound today, so that's great. We won't have to duplicate it.